Hey Miss Wetzler, it's your favorite students, Eli.
And Blake.
And today we're going to be seeing the velocity of the x-axis that we need to roll this ball off this ledge and into this box. Let's do it.
Today we're going to be experimenting with the sport of trick shots. Trick shots are defined as highly unlikely or improbable shots or fun things like bottle flips. Let me show you. Trick shot. Our experiment today is going to be about 2D motion. And 2D motion is about motion in two dimensions, across the x dimension and across the y dimension. Let's see here. The x dimension shows here the distance between our wall and the distance of our bucket. And the y dimension is going to be the height in which the ball falls off first and the height of our bucket.
So if we first look at the velocity in our first dimension, which is horizontally the x-axis, it's going to be constant velocity. So when we start versus when we end, the velocity is the same. And that's what we're going to solve for. In the vertical dimension, which is the y-axis, you start at rest, so the I is originally 0, and then as it moves, it's the acceleration due to gravity that causes it to accelerate downward and eventually land in the bucket. What's up, Miss Wetzler? Now we're going to do the experiment. We're going to roll this ball off this ledge to that box, and we're going to determine the velocity of x mathematically. Let's do it. Yeah!
First, we're going to be measuring the distance on the y-axis. Come on. As you can see, the distance is roughly 45.4 centimeters.
Nice. Next, we have to measure the distance of the x-axis. Let's do it. Looks like we got 90.6 centimeters.
Nice. Full disclosure, both of these measurements will be converted into meters.
Nice.
First, we have to convert our measurements into meters. 45.4 centimeters converts into 0.454 meters. Next, our 90.6 centimeters converts into 0.906 meters.
First, we're going to list the givens for the x-axis. First, we got the distance of x, which is 0.906 meters. Then we have t, and that just puts an equal sign because it's the same for both sides. And we have velocity of x, which we put a question mark because that's what we're solving for. Next, we're going to do the givens for the y-axis. First, we have the initial velocity, vi of y, which is 0. Then we have the distance of y, d of y, which is 0.454 meters. Next, we have time, which is t, which we put an equal sign because it's the same for both. And last, we have the acceleration, which is equal to g, the acceleration due to gravity, which is negative 9.81 meters per second squared. Thank you. Now we're going to solve for t squared on the y-axis. We start with the UAM. T equals VIT plus 1/2 AT squared. Since VI is 0, we can cancel that entire section. So that leaves us with D equals 1/2 GT squared. Because A and G are, G is gravity for acceleration. Okay, so now we want to solve for t squared. So we're going to divide by 1/2 G. That leaves us with t squared equals 2D over G.
Next, we're going to be solving the x term using the equation v of x equals d of x over t. Because we're solving for t, we need to isolate the variable, which equals t equals d of x over v of x. But of course, we're solving for t squared, which means we need to square both sides, giving us t squared equals dx squared over vx. Thank you.
Next, we're going to use the equate method and get rid of t squared in both equations and set them equal to each other. So for one equation, we have dx squared over vx squared, and the other equation, we have 2d over g. So the new equation is dx squared over dx squared equals 2d over g. Next, you got to cross multiply. You get dx squared times g equals 2dy times vx squared. Now we have to isolate the variable of vx squared. So we divide 2t of y from both sides. That equals vx squared equals dx squared times g over 2dy. Lastly, we have to square root both sides. And that way we get vx equals the square root of dx squared times g over 2d of y.
Next, we need to plug in our given. v of x equals the square root of 0.906 meters squared times negative 9.81 meters per second squared over 2 times negative 0.454 meters. Therefore, the velocity of x equals 2.98 meters per second.
We did it. Now we're going to be looking at the graphs of motion. So let's start with a displacement versus time graph for the x-axis. As you can see right here, there is a direct relationship between displacement and time for the x-axis, and it is a linear line. And if you look at the slope is actually the velocity of the x-axis. Now we're going to be looking at the graph of motion for displacement versus time in the y-axis. So if you look at here, you can see that it is a negative parabola. It starts decreasing kind of slowly, and then it starts to decrease more and more until it reaches the displacement equals 0. Now we're going to be looking at the graph of motion for velocity versus time in the x-axis. So we know that the velocity of x is constant, so it's going to be a straight line at the velocity of x. Now we're going to be looking at the graph of motion of velocity versus time for the y-axis. So as you can see here, the graph is going to start at 0, and it's going to decrease linearly. As you can see, the slope is going to be the acceleration due to gravity of negative 9.81 meters per second squared. Now we're going to be looking at the graph of motion of acceleration versus time in the x-axis. So because it's a constant velocity, the acceleration is going to be 0. So it's going to be a straight line that's at y equals 0 the entire time. Now we'll get the graph of motion of acceleration versus time in the y-axis. So as we said before, the acceleration is the acceleration due to gravity, or g, which is negative 9.81 meters per second squared. So it's going to be a straight line that's at negative 9.1 meters per second squared in the y-axis.
As you can see, this is our vector diagram for our velocity of our ball. At t equals 0, the velocity in the y-axis equals 0. However, as time continues in each ball frame, the vector increases in length, which is why the arrows increase in size. However, in the vx direction, the vectors are constant, which is why they're always the same length, moving in the right direction. Now this is our vector diagram for the acceleration of the ball. The acceleration of the y-axis, also known as the effect of gravity, is constant and negative, which is why the arrows are all pointed downwards and are all, of course, the same length. However, the acceleration of the x-axis is not present because it's a constant velocity, which means that there are no vectors. This video was vectacular.